Topic 8 is matrix factorization. One of the key ideas in linear algebra is that we can factor matrices into pieces, and that's going to make thinking about problems and solving problems easier. So for starters, I'm going to try, in this section, I'm going to show that elimination is a type of factorization. And then in the next set of lectures, the ones I've cleverly labeled linear algebra 2, mostly there'll be a little bit on certain types of matrices, but the rest of it will just be on different types of problems and the kind of matrix factorizations that are going to allow us to solve those. So let's look at elimination closely at the 2 by 2 case. So I started out with a matrix A. So this 2, 1, 6, 8 is my matrix A. And I want to turn this into an upper triangular matrix. So I want to introduce a 0 here. And so I'm going to choose an elimination matrix, E21, with a multiplier of 3. And when I pre-multiply A by this elimination matrix, I'll get the 0 in the position that I want. So this one elimination step gives me an upper triangular system. And so because it's upper triangular, I'm going to call it U. And we could think about what's going to happen if I multiply by E inverse. So the inverse, because if I multiply a matrix by its inverse, I get the identity. You can think, if I think of a matrix as operating on another matrix now, so in the first row, I had E21 times A, that's reducing it to an upper triangular matrix. If I wanted to undo that operation, so I could multiply E21 by its inverse, then if I put this matrix up here, that would just be the identity matrix times A. So that should just give me 2, 1, 6, 8, my matrix A back. So if I multiply E inverse 2, 1 with the multiplier of 3, so here I was subtracting 3 times the first row from the second. And here, it's easy to, because I know what undoing it is, because I can think of it just as what is the opposite elimination step. I know exactly how to make this inverse matrix without having to do any computations. So if I say, well, now I want to multiply my upper triangular matrix by this inverse elimination matrix, that should give me A back. And so you can check this if you want to, but take my word for it, it does. And if you look closely at this E21 inverse, so it's 1, 0, 3, 1, it has a 0 up here. So U, I called this an upper triangular matrix because the elements below that diagonal are 0. Here, I'm going to call this matrix L, so it's a lower triangular matrix because the elements above the diagonal are going to be 0. And so U operates on A to give, E21 operates on A to give me U, and E21 inverse operates on U to give me A back. And so if I look closely at this, this is U, and this is L. So I have this factorization. A is equal to L, so I'm trying to highlight the whole matrix, but I can't, L times U. So doing elimination is the same thing as factoring the matrix A into a lower triangular matrix L and an upper triangular matrix U. And then for a 3 by 3 matrix, I would just end up doing, so these are the elimination steps I used in my example that was in, I think it was section 6 today, the first one I did today. So I had E21 introduces a 0 in the second row. E31 introduces a 0 in the third row. and then E32 introduces a 0 in the third row and the second column. And so this is what I needed to do to turn a 3 by 3 matrix into an upper triangular matrix. And so if I wanted to undo that, so by really what I'm trying to do here is multiply by this set of inverses, and no, it's going to go in the opposite order because I want E32. It has to undo what I did last. And so this is why it's very nice that I had this property that when I take the inverse, the order switches. And so my matrix L just becomes the product of these inverses. And I guess it's not clear. So in the 2 by 2 case, it's obvious that I'm going to have a 0 here. These lower triangular matrices have the property that when I multiply them together, the product stays lower triangular. So this is a lower triangular matrix, this is a lower triangular matrix, and this is a lower triangular matrix. When I multiply all three of those together, I get a matrix L that's also going to stay lower triangular. And it turns out it's even better than that. So I labeled my slide here. Seems too good to be true, but is. So it turns out that the strict lower triangular entries of L are just the elimination multipliers. So if I say Lij, that's just going to be the multiplier. So I've been writing the multiplier in parentheses when I write down my elimination matrices. So if I called the multiplier m sub ij, well, that's exactly what I'm going to put in the entries of this matrix L. So Lij gets whatever multiplier I used in the ith, jth elimination. So if I look back at my elimination example, first I had E21, so that was subtracting twice the first row from the second. E31, so subtract minus the first row from the third, or that's the same as adding the first row to the third. And then, E32, which was to subtract the second row from the third. And so I did those three steps. That gave me an upper triangular system. So I end up with this matrix when I look at the inverse of these. So the elimination matrix, I put a minus sign in front of this. For the inverse of the elimination matrix, I just put exactly the multiplier in the. So I put a 2 in the 2, 1 position. I put a negative 1 in the 3, 1 position. So let's see what shows up next. Yeah, so third row, first column gets a negative 1. Oh, dear. Oh, no, that's still right. And then the 3, 2 position, so E32, gets a 1. And then it turns out if I compute the product of these using my matrix multiplication rule, I end up with this matrix L. And so in the L matrix, I don't even have to do this. You can sort of prove ahead of time that if I take the product of these matrices, I just end up with this 2 in this spot, this negative 1 in this spot, and this 1 in this spot. And this holds for even higher dimensions. So I get this L basically for free as I'm doing the elimination step. I don't have to do any computation other than just when I figure out what this elimination matrix should be, I can write the appropriate entry into L. So I can start off with L being the identity matrix. When I do my first elimination step, E21, I just write a 2 in here. Do my second elimination step, E31 of minus 1, I just write the minus 1 in here. And when I do the final elimination step, I write a positive 1 in the third row, second column, so in the 3, 2 position here. That's just what I'm defining them to be. So if they had a minus sign here, so if this was minus 2, it would be the elimination matrix. Right. Okay. And then so if I subtract 2 times the first row from the second, then the inverse of that would be to add 2 times the first row to the second. So there's no minus sign here. Right. And so if you ask a computer program to solve AX equals B, it's probably going to do it in 2 steps. And the steps end up being, first, you factor A into L and U. So you can do this just with the matrix A. So I don't need to do the augmented matrix like I did in my example. And I end up with L and U. So my lower triangular factor and my upper triangular factor. And then I solve the system. So what I first do is solve LC equals B. And so since L is a lower triangular matrix, it's the same idea as back substitution, but now it's forward substitution, just because in the first row, there's only going to be one non-zero coefficient. So I use that to solve for the first element of C. Then I plug that value in and solve for the second element of C, plug those two values in, solve for the third element of C, and so on. And then once I know what C is, I can solve Ux, so U is my upper triangular factor. And I solve for x by solving the system Ux equals C. Again, this is easy because U is already an upper triangular matrix. So I'm just going to solve Ux equals C, not B, by backward substitution. And you can see that this is going to give you the correct answer because you can just multiply Ux equals C. So the second thing I solve, I'll pre-multiply that by L. So I'll start off with Ux equals C. Pre-multiplying by L gives me Lux equals LC. But LC, that's what I got. I got that value of C just by solving LC equals B. So on the right-hand side, I'm going to end up with a B. And then when I get rid of the parentheses here, I'm going to have Lu times x equals B. But Lu is just my factorization of A. So I end up with Lux equals B, or Ax equals B. So this is going to give me the x that solves Ax equals B. So just for a quick example, let's try this with a 2x2 system. So I'll try and solve the system that's represented in matrix form by this. So I have A times x equals B. So my multiplier is going to be a 2. So I want to eliminate this 4 by subtracting twice the first row from the second. And that's going to give me, so the first row stays the same. I know I'm going to get a 0 down here because that's how I've constructed my elimination step. And then this 9 is going to be turned into a 5 because I'm going to subtract 2 times this 2 here. And then I have to do the same thing. I have to do the same thing on the right-hand side. So my 21 is going to get turned into a 5 because I'm going to subtract 2 times 8 from 21. So 21 minus 16 gives me 5. And so if you look at what happened on the right-hand side, that's exactly what I get when I solve my lower triangular system here. So I have my L is going to be the identity matrix, and then the multiplier from my one elimination step. So my elimination step had a multiplier of 2 because I subtracted twice the first row from the second. So my L matrix is going to be identity with a 2 in the 2, 1 position. And then that's going to tell me right away, so 1 times C1 equals 8. I get the 8 here. And then I get 1 times C1 plus 2 times C2 equals 21. Oops. Sorry, 2 times C1 plus 1 times C2 equals 21. And that tells me that C2 has to be equal to 5. So that's, again, 2 times 8 is 16 plus C2 equals 5. 21 minus 16 is 5. And then my upper triangular system, now I have the 8, 5 on the right-hand side that I got from solving my lower triangular system. Well, that's exactly what I wanted to have here in my elimination. And now I only have to do the back substitution to find that x is equal to 3, 1. So it's 5 times x2 is equal to 5. That gives me the 1. And then 2 times x1 plus 2 times x1 plus 2, because x2 is equal to 2, has to be equal to 8. So that means 2x1 has to be equal to 6, or x1 has to be equal to 3. So LU factorization elimination factors A into LU, so that's what LU factorization is. It also turns out that the upper triangle U, upper triangular U, has the pivots on its diagonal. And the lower triangle L always is going to have 1s on its diagonal because I'm getting this from an identity matrix, and then I'm just plugging in the lower triangular values that are my multipliers. So if I know L always has 1s on the diagonal, there's no reason for me to store those in memory or even keep track of them. And if I know U always has 0s below the main diagonal, then I could use those elements below the main diagonal for anything I want to, because if I were writing an algorithm, if I know something's 0, my algorithm's just going to be faster if I never touch it. So if I know that a value is 0, there's no point in multiplying something times a value I know is 0 and then adding it. So I just ignore it, and that has exactly the same effect. So L has also these multipliers Lj. And if I want to consider what the computational cost of elimination is, so there's actually two costs I want to keep in mind. One is the number of computations I have to do. But another sort of equally important one, in my opinion actually, so I used to be a programmer for a while, I think this is more important, is to use less memory. So the computational cost, elimination on A requires 1/3 n cubed multiplications and 1/3 n cubed subtractions. This is sort of roughly what it's going to take. But suppose I factor A, so I have a dense matrix A. So dense just means that every element is non-zero, or could be, into a lower triangular matrix L. So I have only zeros up here. I have 1s down the diagonal. And then the important numbers are only in the lower triangle, strictly below the diagonal. And upper triangular matrix that I can write with the pivots down the diagonal, and then some upper triangular entries. But I have these three values down here that I can kind of use for some other purpose. And it turns out I have exactly those three values in my matrix L that kind of determine what L is. Everything else, the diagonal is determined, and everything above the diagonal is determined. So I can actually write this whole thing in the same space that I would use to store my matrix A. So if I look at the first row, this would be the same as the first row of A, because when I do elimination, if there's a non-zero value here that I can use as my pivot, so this is kind of assuming there is, then I'm going to leave the first row alone. So this row stays the same. And then I'm going to look at A21 and my pivot A11, and I'm going to choose a multiplier. And as soon as I've chosen that multiplier, I know if I do an elimination step, this value is going to be 0. So once I know what the multiplier is, I might as well just write that down here. So if I was doing this on a chalkboard, I figure out what the multiplier is. I erase this value A21, and I write the multiplier there. Then when I do the elimination, because I know that this is going to become a 0, because that's how I've constructed the multiplier, I don't need to do any math on that. So it's not going to touch this value of L21 that I've stored in the lower triangle. And I'll just do the elimination on these two elements. And that'll give me the second pivot and then some other number in the upper triangle. And then if I continue in that way, I'm going to end up with the LU factor stored in exactly the same memory that I started out using to store my matrix A. So if you're doing this on a chalkboard, you only ever have to erase one number at a time, which is different than the way you probably had to do the exercise for the first quiz today, where you had to write out the system every time you did the elimination. And then also, you end up doing less mathematics, because you're never doing the operations that would lead to the zeros that would appear down below in this matrix here. And so that's actually pretty good, because I think in the two quiz questions you've done so far, you've probably realized that you're making, even when I'm asking you to do relatively simple additions and multiplications, probably a lot of mistakes. So, if you're doing things by hand, it's still a good idea. to use less memory and to do the fewest number of computations possible, because every computation is an opportunity to make a mistake. And if you're programming a computer, your algorithm's just going to be faster if you're not touching memory that you don't need to.